Welcome. So this is 48B video 1. So we're doing courses 2048 and this is chapter B, and the title of this one is Motion in One Dimension, and it's the first part of this chapter. My name is Anthony Bonaquisti and I'm the course instructor. And we're going to talk about today is displacement, velocity and acceleration. We're going to talk about instantaneous velocity and acceleration and what that means. We'll talk about speeding up and slowing down. There's some misconceptions about that. And we'll talk about motion graphs. So we'll divide this up into a couple of videos. So let's just look at this. It says the displacement of an object is a vector. Well, it means it's got a magnitude, that's a size, and also a direction. So with a vector you can say it points in a given direction. I couldn't say 5 kilograms points to the left because kilograms aren't a vector. I couldn't say 3 seconds points to the right because time is not a vector. But I can say this force 5 newtons points to the left, or I could say this velocity 3 meters per second points to the right. So velocities have a magnitude, they have a size, a numerical value, and a direction. And it's a direction in a room. You cannot use it's a positive and a negative, so it must be a vector, because that's just an address. So you've got to be able to visualize it pointing in a room. The distance traveled, on the other hand, is a scalar. It only has magnitude. It is the sum of all parts of the motion without regard for the direction of travel. So if I go on a journey, then the distance traveled is a certain path length, whereas the vector would be the distance directly from the beginning to the end. So this was what I would call my displacement, and this is what I would call my distance traveled. I shouldn't say dt like that, should I? Let's say big D, big T, so I don't get it confused with other things. So the equation is displacement. Delta x to me is one word and it means displacement. So my displacement is equal to my final position minus my initial position. And we always go final minus initial. So here's a typical problem. An object starts at +3 meters. What's not said is we're on a number line and we start off from here and we're at +3. It moves 7 meters to the right. So we go along here and now I know I'm at +10. It then moves to a point located at -12 meters. So it goes all the way back here until it's at -12 meters. Notice -12 meters is an address. That 7 meters is a displacement. So you got to read the words and you got to be able to discern exactly what the words are meaning. I can move you about this number line by telling you how far you move to the right or how far you move to the left. I could tell you that you travel to the right at a given speed for a given time, or you travel to the left for a given speed for a given time. Or I can give you a final address and say, hey, figure out what you need to do. So there's 3 basic ways I can move you about this number line. Notice I have arrows because they're vectors. They happen to be along a straight line, but they're vectors. And the vector has a beginning and an end, and the end always has an arrowhead on it. And notice please that I mark the start and I mark the end. So I say, well, my displacement is equal to x final minus x initial. So my displacement is equal to, I look at my diagram, I'm looking for a position, looking for an address. I look and the end is -12. and then minus, and I look at the diagram and I look here and I say this is plus 3, and so mathematically now I say I have minus 12 minus plus 3 is minus 15, and it needs meters, it needs a unit. And incidentally, I can represent that on the diagram as a vector which goes from the start point to the end point. That's my delta x, and it's 15 meters long, and it points in a negative direction. Just a few words here. This negative there is an operator. It's a mathematical symbol. This negative there is part of an address. Minus 12 is an address. Plus 12 is a different address. So I try to make sure I don't mix the two up. So I put my vectors in parentheses. So I know that minus is part of an address. This minus is an operator. Distance traveled is actually a little bit harder to figure out. Distance traveled. Again, I'm going to look at my diagram. And the first part of my journey, I went from 3 to 10, which is 7 meters long. And then I went from plus 10 to minus 12. Let's break this up into 2 bits. I went from plus 10 to the origin, which is 10 units long, and I went from the origin to minus 12, which is 12 units long. So my distance traveled is 12 and 7 makes 19, 29 meters. There's not really a formulaic equation for distance traveled. It is just the sum of all the bits of the journey. And sometimes they're a little bit harder to work out than the actual displacement is. We prefer the displacement in science because it turns out that in many parts of science we don't have to deal with friction. So the distance traveled does not matter. It's the change in position that matters. And that's given by the displacement. I think of it being like a bank manager. A bank manager doesn't necessarily care about how many times you put money in or take money out of your bank account. All they care about is the ending balance and the beginning balance. It's the same with displacement. Okay, so let's think about average velocity and speed. The average velocity is a vector. It's got a magnitude and a direction. It has a magnitude and direction. And we say average, we put this little balancing sign above, and we say the average velocity equals my change in position, which is my displacement, divided by my duration, which is my change in time. And if I want to write this out more longhand, I'd say my final position minus my initial position divided by my final time minus my initial time. And sometimes I'll give you the displacement, or I'll give you the 2 positions, and sometimes I'll give you the duration or the time interval, or I'll give you the 2 times. But you've got to be able to work those things out. And compare this with the average speed, which is a scalar, and it's the distance traveled divided by the time taken. So let's try this typical question. An object starts at plus 9, so let's have 0 here, and we'll have plus 9 here, and I start here. Okay, so let's call it S. And then the object moves 6 meters to the right, so I've gone here to plus 15, and so I'm there. And the object, in 4 seconds. So I need to somehow keep track of the time. So let's get rid of this S. And let's say that the clock said 0 when we began. So now the clock would say 4 seconds. I could have said that the clock said 10 seconds when we began, in which case I'd put down 14 seconds for this second point. It doesn't matter, as long as I keep track. The object is stationary for 1 second, so now my clock is saying 5. The object moves 3 meters to the right, to the left, in 2 seconds, so my clock is now saying 7. And I move 3 meters to the left, so I'm at plus 12 meters. So my journey's over to one side of my number line. Let's work some things out. Average velocity. My average velocity is equal to my displacement divided by my duration, which equals my final position minus my initial position divided by my final time, t final minus my t initial. And this equals my final position. I'm looking at the diagram, it's plus 12. I'm going to take away from that my initial position, which is plus 9, and then I divide it by my final time. I'm looking at the diagram is 7 minus my initial time is 0. And if I think about that, 12 minus plus 9 is plus 3 divided by 7. And so we have 3 plus 3 divided by 7. So my average velocity 0.429, and notice it's a positive. I like to put the positives in. That means it's moving to the right, and I'm always sure to put my numbers in. So that's meters per second. My average speed, speed is going to equal my distance traveled over my time taken, which equals, and now I'm going to do this distance travel business again. I went from 9 to 15, so that was 6. I was stationary for a second, that doesn't count. And then I went from 15 to 12, so that was 3. And then my time taken, again I'm looking at the diagram, and I have my 7 minus my 0. So this will be 9 over 3, 9 over 7, and so speed is equal to 9 divided by 7, which equals 1.286 meters per second. I don't bother with the positive sign because it's a speed, so it's going to be positive. It doesn't have a direction. But I make sure I put down my units and I make sure it makes sense. Cool. I can do the next thing, which is average acceleration, and it's a vector. It has a direction and a magnitude. And it's the acceleration is equal to my change in velocity over my duration, which equals my final velocity minus my initial velocity over my final time minus my initial time. We can also talk about the scalar of acceleration, and there's not a common science word for it. I use the term pickup, like this truck has a lot of pickup. It can accelerate quickly. So pickup is a scalar. It only has magnitude. It's the change in speed divided by the change in time. So let's imagine our number line again. I say an object has a velocity of plus 5 at t equals plus 7. I don't give you a position. Sometimes I will, but in this case I haven't. So just pick a point and say, okay, this is 7 seconds. And I'm going v initial, and that's plus 5 meters per second. And then the object has a velocity of minus 17 meters per second at t equals 11 seconds, and that's my v final. And it wants to know what is the average acceleration. My average acceleration is equal to my change in velocity over my duration, which equals v final minus v initial over t final minus t initial, which equals, looking at your diagram, minus 17 minus plus 5 over final time is 11 seconds minus my initial time. My initial time was not 0. I began the journey at 7 seconds. The clock was reading 7 when I began. No law says I have to begin when the clock says 0. So this is going to be minus 17 minus 5 is minus 22. And this is going to be 11 minus 7, which is 4. So then I say my acceleration is equal to, well, let's have a look, minus 4 5s are 20, carry the 2, 4 5s are 20 meters per second squared. So there's my answer for that. So notice we don't have to start the clock off at 0. We can basically start the clock whenever we like, and from the wording and our visualization we have to figure out when the journey begins and the journey ends. For pickup, my pickup is equal to basically well, my change in velocity, my change in speed. So that's going to be 17 minus 5 over my change in time, which would be 4. So that's going to be something like 12 over 4, which is 3 meters per second squared. Not really got a good meaning for that. We don't use it much in science. We'll use distance traveled, we'll use speed, but we don't use pickup much at all. Here's a typical example. At t equals 2 seconds, a car is at minus 8. So this is at 2, and the car is at minus 8 meters. At t equals 8 seconds, it is at plus 4. So here's plus 4, and the clock is saying 8 seconds. At t equals 9 seconds, it is at minus 12. So here we are back here at minus 12, and it's saying 9 seconds. What's the displacement as a result of this journey, and what is the distance travelled? My displacement is equal to my final position minus my initial position. My displacement is equal to, it's going to be, looking at my diagram, minus 12 minus 8, which equals minus 4 meters, and I can represent that on the diagram just to double check by going from the beginning to the end of the journey, and it's only a short distance, and yeah, it's in a negative direction. My distance traveled, well, I went from minus 8 to 0, which is 8. I went from 0 to 4, which is 4. I went from 4 to 0, which is another 4, and then I went from 0 to minus 12, which is another 12. My distance traveled is equal to 2 8s are 16, 26, 28 meters. People, especially people who don't draw diagrams, tend to get these types of questions wrong, because notice I mention a plus 4 and I mention a minus 12, but I don't mention going through the zero. So if you're glancing at the words, you won't necessarily realize that you've got to go to the 4 and then come back again. So people will sometimes forget the number there because it's not inferred from the words until you draw the diagram. Why do I keep writing these equations down? Because I want to remember them. I want them to be in my memory, in hardwired basically in my memory. Okay, let's look at this other typical question. So here's our number line at t equals 5 seconds. So when the clock says 5, I'm at minus 16 meters. Then it says at t equals 9 seconds, it is located 6 meters to the right of the starting point. So I'm going to be 6 meters over here, which is minus 10. And the clock says 9. After another 2 seconds, it is at minus 12. So minus 12. And now the clock is saying 11. What is the average velocity that results from this journey? So I'm going to say my average velocity is equal to my displacement over my duration, which is my final position minus my initial position over my final time minus my initial time, which equals, well, my final position is minus 12 and my initial position is minus 16, and my time, my final time is 11, and my initial time for this journey is 5. So that's going to be 12 minus minus 16 is plus 4, and 11 minus 5 is 6. So that equals 0.667 meters per second, and it's positive, meaning that it's pointing to the right. Can you see the pattern? I'm reading the words, I'm drawing a diagram. I'm drawing a diagram, I'm getting an equation. I'm extending the equation, I'm substituting in numbers, and then doing my math. The math is the last little bit. Let's take a break there. Thank you.